Hi and welcome to John's Maths Book. In this video we're going to be taking a look at Rolle's theorem. If you like the video then please hit the like button and I'd be delighted and honoured if you'd subscribe to the channel. Without further ado, let's go over to the whiteboard. Rolle's theorem states that if a function f is continuous on the closed interval ab and differentiable on the open interval ab, if f of a is equal to f of b, then there is at least one value c on the open interval ab where f prime of c is equal to 0. Let's try and unpack this. It describes a function f of x which is continuous on a closed interval a and b. So I've drawn a function f of x and I've marked the interval ab. The first thing to note is that the closed interval includes the endpoints. So in this case the endpoints are a and b. It then refers to a continuous function on this closed interval. Intuitively, this means that you can draw the function without taking your pen off the paper, so there are no jumps or holes in the function. Please check out my video on how to identify continuous and discontinuous functions. Next, it says the function must be differentiable on the open interval, which means that tangents to the curve must exist on the open interval at every point. Then, if f of a is equal to f of b, so the y values at x equals a and x equals b are the same, then there is at least one value, let's call it c, on the x-axis between a and b, but not including a and b, where f prime of c, so that's the derivative of f, is equal to 0. This means that there is at least one tangent to the curve which is horizontal or parallel to the x-axis, as shown here in the diagram. So let's look at some examples of how we apply Rolle's theorem. So we have a function here, f of x, which is 2x squared plus x plus 1, and it's defined over the closed interval from -1 to 0.5. We first need to check whether Rolle's theorem applies to this function over this interval. So as we can see, f of x is a polynomial, so it's continuous and has no breaks, and it's a smooth curve, so we can take the derivative anywhere between -1 and 0.5. So now let's check the y values at -1 and 0.5. For Rolle's theorem to apply across this interval, the y values must be equal at the end points of the interval. So the end points in this case are -1 and 0.5. So if I plug the end point of -1 into the function, I get 2 multiplied by -1 squared plus, and then -1, and then +1. And if we evaluate all that, it comes out as 2. And now if I plug the endpoint 0.5 into the function, I get 2 multiplied by 0.5 squared plus 0.5 plus 1, which is equal to 2. So we can confirm that the y values at the endpoints of -1 and 0.5 are the same. So the y values in this case are both equal to 2. So this function over the interval -1 and 0.5 passes all the tests for Rolle's theorem to apply. Given this, we now know that f prime of x is equal to 0. So f prime of x, or the derivative of x in this case, is 4x plus 1. So we can set this equal to 0 and solve the equation for x. And so solving this equation for x, we see that x comes out to be -1/4. So on our graph of f of x, I've marked where the tangent to the curve is horizontal to the x-axis. And as you can see, it occurs at -1/4 or -0.25. Now let's take a look at this function f of x and see why Rolle's theorem does not apply. The function x squared plus 1 divided by x is defined on the closed interval -1 to 1. So let's apply the tests for Rolle's theorem. The first test is that the function must be continuous across the closed interval. So the closed interval here is -1 to 1. Within that interval, we have 0. And as we can see from the function, we have x squared plus 1 divided by x. So if we substitute 0 in for x into the function, we'll see that the function is undefined. This is clear from the sketch of the function, where at 0 we have a vertical asymptote. So this function across this interval fails the test, so we cannot apply Rolle's theorem in this case.